Hi, John Capobianco here, and today we're going to be looking at trends in AI ops, so artificial intelligence operations. This might sound new to you. This is an evolution of the continuous progression in operations. So today we're going to be specifically looking at a technique, a highly evolved and a highly practice technique known as retrieval augmented fine-tuning, RAFT. So, first we have to break down RAG, retrieval augmented generation, but not just RAG, different approaches to retrieval augmentation. Next, we're going to look into the world of fine-tuning, RAFT, retrieval augmented fine-tuning. I'm going to give you a real example of how this is done on ChatGPT and the OpenAI fine-tuning platform. Also, we're going to explore what I consider the world's first network language model, NLM. Now, we've heard of LLMs, large language models, SLMs, small language models. We're going to be looking at a highly fine-tuned version of an open source model that's been mutated and trained with network data to create the first network language models. So let's dive in to RAFT in this Trends of AI Ops Part 1, I guess, in this series. Thank you. So again, hi, my name is John Capobianco and I'm here with Selector AI talking about trends in AI ops, and we're going to focus on retrieval augmented fine-tuning today. So, before we get started, we're going to talk a little bit about Selector, an industry-leading AI ops for operational intelligence. And it really is artificial intelligence merged with operational insights to drive this to humans using machine learning and artificial intelligence. Agenda for today: some brief introductions, an overview of AI ops, implementing AI ops, focusing on a technical deeper dive on RAFT and various retrieval approaches and Selector's fine-tuning approach to creating a network language model, and some use case exploration, including something we're going to call the tornado incident, when something really bad happens. And then we're going to come to some conclusions. So, Selector at a glance. Selector was founded in 2019 by the founding team that led routing and switching at Juniper Networks. Highly esteemed founders, and they've built up this organization of over 100 people so far, from networking, applications, AI, machine learning, from across the industry. Juniper, Cisco, Google, VMware, Nutanix, and more, and others. And really has become a Gartner recommended vendor for network AI ops. And in my personal opinion and experience, really one of the only and first companies to truly harness the power of machine learning and generative AI. So who am I? My name is John Capobianco. I'm a product marketing evangelist, and that's what I'm trying to do here today, is evangelize artificial intelligence, generally speaking, at a high level, and machine learning. But as we get closer, evangelizing Selector's implementation of machine learning and AI ops and generative AI. So I used to be with Cisco as a technical leader in AI. Prior to that, I was a senior network architect with the Parliament of Canada, the House of Commons. While I was there, in around 2014, about 10 years ago, I started to adopt and embrace network automation. In 2019, I self-published Automate Your Network, a book about Ansible and Cisco network automation. And I just recently published through Cisco Press a PyETS book, which is interesting because chapter 23 of that book is actually about artificial intelligence and how to tie it in to network automation. So let's do a quick history of operations and then artificial intelligence. So the evolution of operations, we started with traditional operations, which I would suggest lasted until about 2020, the year 2000, 2002-ish. And in those days, it was heavily reliant on syslogs and SNMP and custom solutions and maybe certain third-party vendors to help you monitor and operate your network. It was heavily reliant on manual effort, and it was very reactive. Now, in the early 2000s, the world of software development and software engineering went through some radical overhauls and some changes. You may have heard of DevOps, right? This tried to break away from waterfall as a process, each process, continuing and waterfalling down until eventually you end up with a product, into more of an agile approach, more of this DevOps approach where we plan, code, build, test, release, deploy, operate, and then monitor, and then start the cycle all over again continuously. Speaking of continuously, DevOps introduced this idea of continuous integration and continuous delivery, often found through the forms of GitOps or GitHub or Git version and source control, where when we merge in new code that's been tested into production, it kicks off a series of delivery mechanisms, continuously integrating and continuously delivering code. Well, quite a few years later, the world of networking tried to and started to adopt, I would argue in 2013, 2014, network DevOps, where we're going to take that same idea of agility and pipelines and breaking down silos, where the developers and the operators are not in separate parts of the organization. They're working collaboratively. Can we make the network engineers work collaboratively with developers and operators in this CI/CD, continuous integration, continuous delivery framework, and apply best practices learned from 7 to 12 years of the software industry using these practices and apply it to our infrastructure? So things like infrastructure as code, often expressed as YAML. YAML ain't markdown language, a recursive acronym. Now YAML it's not really code per se, it's structured text, but it can be interpreted and used in things like Ansible and other technologies. This led to network automation and other infrastructure automation, not just with Ansible, but with Terraform and with Python scripts primarily and Python code. And we further reduced the silos and brought the network engineers and architects and operators closer together, and also closer to the software engineers in the enterprise, so they can collaborate on the best way to implement pipelines and code and other things that network engineers may lack the familiarity with. Now, what is the next natural step from network automation and net DevOps? I really believe, and it's here today in Selector, is AI Ops, where we're going to incorporate things like machine learning and generative AI and predictive AI into our operations. Now, this is not a displacement of humans. This is an augmentation of humans. Just like network automation augmented humans and didn't really displace a large number of network engineers. AI Ops is really about the human experience and how we can deal with things at such a massive scale and massive complexity in the modern enterprise today. Well, now we have things like copilots to help us and machine learning to take the massive amounts of data and connect the dots and to help us. And we can have natural language interfaces where we can speak to this copilot just as we would a colleague or an expert or an escalation ticket, right? We can truly interact with a new member of our team that is much more capable simply because it can synthesize so much more data than we can as human beings. So let's take a deeper dive into these astonishing capabilities. So I don't believe that rapid change comes in normal times. And we've hit a technology inflection point with artificial intelligence. And I would argue November of 2022, when ChatGPT 3.5 first became available, was when we hit this inflection point. Now, we're only, let's call it 2 or 3 millimeters away from the inflection point on this timeline. But things, as you can recognize, are rapidly changing. And we are moving towards this new green hockey stick evolution of technology. And the red is obsolete methodology, wasted human hours, approaches that don't simply make any more sense now that we have this new capability. Those things are going to start to fall off. Now, there is a point a little further down this timeline where it seems like this is happening extremely rapidly. We are approaching that. We are somewhere in between just after the inflection point and the huge uplift in the adoption of this new technology. Now, I'm paying very close attention to the world's reaction and society's reaction and social media's reaction and certain people's reaction to this inflection point. And I'd like to draw some comparisons to inflection points in my lifetime. Okay, so the very first thing is computing. Now, there are people still in the industry from the 70s, punch cards and tape drives, and sort of an analog to digital conversion. For me, it was 1984. An IBM clone is what it was called. It wasn't directly from IBM. It was a 286 chip with a hard drive and RAM and a dial-up modem that we assembled ourselves with parts. Now, in that early days in the 80s, it was sort of seen as a hobby, like ham radio or model trains or something. Who's going to need a computer in their house? Those are things and challenges to computing that I've heard in my lifetime. And now look at how many computers, right? It's not really even a second thought that you're going to have a computer, at least one computer, in your home today. And all of the things and amazing and incredible things we can do, like record this video and put it up on YouTube. Now, the internet went through even higher scrutiny because it was an even more dramatic inflection point, right? Some of the challenges were things like, so what, this is just an online garage sale. A computer, right? I dial up to the internet and I'm able to go to eBay. Like, so what, right? There's famous quotes that the internet's economic impact won't be any greater than the fax machine. There was the .com crash. There's been heavy detraction against the internet since its inception in the early 1990s. And as we know, right, look at the internet today. It's not even a second thought to us. It's second nature to use the internet today. Now, mobility went through similar scrutiny. Who needs a computer on their phone? Right? My phone is for making phone calls, not for taking pictures, not for searching the internet, right? And now look at the boom in mobility. Now the cloud, what? I'm going to put my stuff on someone else's computer, so what? And now look at all of the cloud services. Look at the streaming services. Look at our reliance as human beings on these cloud services and the massive advancements in human experience because of cloud services and mobility and internet and computing. Well, now we come to artificial intelligence. There's no value in it. It's not worth the investment. There's no ROI. It's stupid. It makes mistakes. It's wrong. You're going to see a lot of detraction against AI And again, as we climb up the inflection point, I believe there's an equal level of resistance against the technology in its early phases. And this inflection point may only last until 2025. There might be only another year before we get to narrowing artificial intelligence and true generative AI, AGI, and then a widening AI. And we're just going to hit more and more inflection points. But right now, we are in this early middle of the inflection point period with artificial intelligence. Now, I'm not going to read all of this. You can skim these over yourself with your eyes. But we have seen an explosion of devices around the world. Every human being has 3 to 5. Some people have 10, 20. Who knows how many devices there really are? Enterprises with more and more things moving to IoT, cameras and door swipes and payment systems and sensors and stoves, everything you could think of, microphones, sound systems, multimedia capabilities. And then the boom in mobility on top of that, right? Now we have this also have an explosion as operators of applications and therefore data sources. Now this is just a sample of the data sources that Selector has proven we can ingest, and there's many, many more. But imagine a human being and what you're asking a human being to be capable of, to be able to interrogate and understand and interface with and look at logs and look at events, look at metrics, look at configuration data from hundreds of data sources and different applications. So what? So what about this explosion? What does that mean? Well, I don't think, and I think it's pretty conclusive, that we can just throw more and more humans at this problem. As we scale more applications, as we add more buildings to our enterprise or campus, as we add data centers, as we add racks, let's just add more and more people and train them up to understand our stack. We also have this new capability of artificial intelligence to help us solve critical operational challenges. Now, the first big challenge is the collection of the data from any source at all, right? And it's heterogeneous data at the same time. Things are not all the same. Configurations look much different than alerts and logs and events, and then the numerical representation and metrics. We need to collect it all and also normalize it for our machine learning. Now, humans cannot simply do this. It takes more and more teams. Okay, you look at the logs. I'm going to look at the logs. Someone's going to look at the alerts. Someone check the config, the change management approval board and see if there's any changes that happened tonight or yesterday. Someone can try to maybe look at the metrics and see if there's any spikes or anomalies. It's just too much. It really is too much at the scale and complexity of the systems that our enterprise relies on, our customers rely on. Now, the next thing is, so even if we can collect all this data, and I'm sure you're already collecting this data in syslog receivers, in NetFlow receivers, in syslog or SNMP traps, and as well as maybe a CMDB, a configuration management database, maybe an IPAM, maybe an IP address management tool, maybe an event capture utility, right? Maybe you're streaming telemetry in for metrics. Even if we have millions of data sources and, megabits and hundreds of megabits of data, how can we correlate any of that information across these different silos to get some insights, right? There is no current way to get automated insights if we throw all this data at a system. Is there any way to automate, to correlate these events and to connect the dots for us to do things that humans aren't necessarily capable of doing or noticing without a lot of time and effort and manual scraping of logs or using maybe regular expression or something. So can we correlate these things to get to a quick root cause to remediate the problem? Now, I think anyone in operations will tell you that remediating a problem, actually correcting the issue, is maybe 3% of the effort. 97 to 99% of the effort goes into discovering what the root cause is, what needs to be fixed. Actually, implementing a fix takes literally no time at all most of the time. Revert the configuration, correct the configuration, replace an optic, contact the ISP. There's certain things that once you know what the problem is, it's self-evident how to heal from that. The other thing is, we work in these silos, as I've mentioned, and we have different specialties as human beings. Someone might be the expert in the load balancing. The security team focuses on the firewalls. The network engineers really know the routing table and the traffic flows. The application developers know the application stack. And on and on and on, these different silos. So when problems occur, we try to come together, maybe in a war room type scenario or through instant messaging or email or alerting type systems, but we really work independently and we don't have any way to unify these silos. The natural capabilities of having a central team member that understands all of the individual silos with varying degrees of expertise, depending on if it's a junior or a senior or a CTO or a user who's asking the questions, this central team member can converse with you back in human language that you can understand. So we can include this as a team member when we're trying to solve problems. Let's ask the AI, right? Together. So it really does bring people together, having this new co-pilot on your team. Now, in the selector pipeline, there is machine learning at every stage, and I'll show you the pipeline soon, but I wanted to show you some of the problems that we're trying to solve, real-world problems, such as mean time to detection, and mean time to response, and even mean time to innocence, and why we're using machine learning. Now I'm going to steal, you see some examples of regular expression on here. Instead, we can use natural language and machine learning now. And we've evolved past these complex string matching with regular expression. As the saying goes from 1997 on the old AltNet days, a person decides to solve a problem with regex, now that person has two problems, right? But there's also proactive alerting. There's avoiding manual correlation of all these siloed alarms and alerts and events and metrics. And we can reduce the complexity of requesting the information we need, right? We're not talking about you having to learn a particular domain-specific language, a DSL, or a specific query language, a QL. We really provide a natural language user experience, which in turn responds with human natural language. So I spoke of the pipeline. Now let's take a step back. Forget about AI, forget about ML. What would a human do, right? Well, we would look at our metrics or logs or events. We would try to connect that to our metadata and our CMDB to maybe isolate something in a geolocation or a particular rack or data center or interface or site, right? We would try to do that as humans with all this raw data. And we would really, in our minds, sort out green and red events, things that we think are normal and we can discard, and things that are anomalous or violate certain baselines or understanding we might have of the network. So we come from white, a sea of noise, into sort of our estimation of what is healthy and what is abnormal, We then try to cluster and correlate those violations across maybe different silos, right? We've noticed that we lost BGP neighbors. We also noticed that there was a firewall configuration change an hour ago, right? Or we've lost LLDP, OSPF neighbors between two routers. There was an interface failure 3 minutes ago, right? So as humans, we try to do this the best that we can, the best to our team's ability, the best to our certification level or our training or our domain-specific knowledge. Let's call it our intuition. Finally, we're going to maybe raise the incident, open the ticket with ServiceNow or our ITSM. We're going to maybe send some messages into Slack rooms or Slack channels or Teams or some other collaboration suite. We may even trigger some automation if we have it to remediate this problem, or go in ourselves and undo the change, or fix the problem, or issue the ticket to our peer or our ISP or our neighbor, right? Or get a hold of the developers if it's an application layer problem. Now, how does the artificial intelligence help? Well, that is what the Selector AI is doing. We're going to take massive amounts of data, as much data really as you can throw at this problem, from a variety of different sources. Using the machine learning algorithms, we're going to use the metrics to create automatic baselines. 1. 2, anything that is sentences, anything we can mine for logs, we're going to mine those logs. Using the smart metrics, we identify that green-red scenario and filter out anything that is good, because we don't really care about what is good. We're trying to find issues and problems. So show me what is an anomaly or a violation here. This is going to dramatically reduce mean time to innocence, by the way. If we can throw out what's good and only see what's bad, we can really truly identify, it's a problem with the load balancer. Oh, it's a problem with the PE router, whatever the issue might be, because we've already reduced it down to violations. Well, we're going to go a step further and do collaborative filtering to reduce the mean time to detection. And and I'm going to talk about some of the techniques in a little bit, the correlations and the probable root cause. Let's connect these things into clusters. We're going to cluster things based on certain tags and certain other features and identifiable named entities, and we're going to connect these dots into correlations. The next thing we can do is deal with the incident. Now that we have the root cause, and we can do the mean time to remediation reduction here by issuing a smart alert, by creating an incident in our ITSM or in the cloud, by alerting the right people with smart information in a human context because we're using natural language here, or even enter a closed loop automation where we can trigger an Ansible playbook, a Terraform piece of code, a PyTS job, or other Python script. We can make REST API calls. Whatever we need to do here, we can automate this incident response, right? Now, this is really remarkable, and it actually has, I will show you this pipeline. So keep this pipeline in the back of your mind, this sort of 5-step process, as we look a little bit deeper at how this is accomplished. So let's focus on some AI ML now. And really, as machines, there are, from a network's perspective, or application even, we have metrics, which are sets of numbers, and we have logs, which are sentences. Now, AI happens to be very good at dealing with large sets of numbers and dealing with sentences, right? So what we can do with this is with the metrics in particular, we can set up automatic baselining that includes seasonality with trend detection. Meaning if there's a Friday night backup and the traffic gets saturated for 4 hours while it's on the wire, this will detect that trend. Monday morning, there's a spike in traffic, right? So we have this automatic thresholding from the metrics that also makes it very easy to detect anomalies, anything outside of this automatic baseline. Now the correlations, again, we spoke about this, we're going to make graphs, visual graphs and knowledge graphs from the various metrics and mined logs to create those correlations, ultimately surfacing root causes. Now, using text to events with natural language techniques, we're going to look at this a little deeper in a minute, we can mine logs for events that a natural language would pick up and that humans can quite easily understand. Finally, we have this nice co-pilot system, which in both directions, if I go back to the pipeline, we can start from the right and work our way left with human natural conversations. So here we're asking for a device status, and we can see the current status is fine with a single violation. Might need to take action for node name, and there's the node name. And we see the single violation in the honeycomb visual interpretation. Now, another thing that we can do with this machine learning capability is set up a ping sweep. So every device on the left, all of the rows, have a matching column, and there is no ping to itself. So that's why we see the white line cutting through the diagonal. But we can see various latency surfacing between this ping sweep. So, site AWS trying to ping some other server, we can blow it up and look at the anomaly and that it's crossed over the automatic baselining. Now, in terms of log mining, we really want to extract named entities, NERs, named entity recognition, where we're going to tag things that are known entities, right? Or named entities, IP addresses, autonomous system numbers, the actual event. We're going to try to normalize all of this in our training and cluster any like or similar logs, extract those named entities, and then process it and fine-tune the log model. And we'll come to fine-tuning later. But this really is a retrieval augmented approach where we're retrieving syslogs, normalizing them and clustering them, and then fine-tuning a model. Once we fine-tune this information into the model, we can now do inference against the normalized data and do lookups and mine the data to find those BGP flaps, interface downs, etc., with natural language moving forward. Now, metadata is a key part of Selector's stack. It's not just enough to have the raw metrics and logs to connect and make these correlations. We really want to include the metadata from things like Netbox or Nautobot or your own IPAMs, your own CMDBs, any piece of metadata that we can attach to these events and alerts and configurations is going to improve the outcome of the machine learning, where we can do the natural language correlation, right? Why is guest Wi-Fi down in Denver? Well, we've had the metadata, which enhances the lookup capability and the SQL queries. Now, here's what this correlation looks like. Once we've connected all the dots, we can see that in this case, event 1, the root cause has caused event 2 and event 3, and each of those events have their own metadata and mined logs and metrics associated with them. But event 2 and event 3 are not connected. Now, how many times have humans looked at event 2 or 3 and connected it to the other event where it should have been related back to event 1? Or how many tickets do we need to create with all of these sub-events instead of making a single smart alert that says, here's event 1, which has caused event 2 and event 3. So we normalize this out into JavaScript object notation, JSON, which then we can trigger that automation stack at the end of the pipeline. Collaboration suites like Slack and Teams, closed loop automation, ITSM, instant alerting, smart alerting. But it also works in the reverse direction. Coming from Slack or Teams, I can make a call here with a natural language that will tie me back to events 1, 2, or 3. Have there been any events in the last 15 minutes? Yes, right? And it will tie it back to this. So let's look at the actual underlying approaches here. Again, that retrieval augmented fine-tuning that I was talking about. So let's first try to understand retrieval augmented generation. Now, this is probably the best image that I've found on the internet, and it's from the LangChain documentation. Now, as a sidebar, LangChain is an open source framework that's similar to Django or PyTS or other Python frameworks. Batteries included, scaffolding included, automation code in Python to do things with artificial intelligence. So when people talk about RAG, and this is a pretty simplistic example, we have a source. It could be a PDF, could be a Word document, a PowerPoint, an Excel, could be HTML code, could be a YouTube video. I've even done it with JavaScript object notation, JSON, which is what a lot of technologists use in a RAG pipeline, is their data as structured text. So we're going to load it and transform it, right? So a JSON loader or a YouTube loader, and then transform is to take the large amounts of text and turn them into sentences, sentence level chunks of text. Now, when we need a model here, an embeddings model, to turn those chunks of text into vectors, which is a mathematical representation of floating point number, a series of floating point numbers, that is the mathematic representation of the chunks of text. Okay, you follow me so far? Once we have all of that, the vectors, we need to store it somewhere in a database. So we use a vector store. Now there are a variety of vector stores: Elastic, Postgres, Chroma, Pinecone, Weaviate. You get to pick your vector store. Finally, we get the LLM involved, or the NLM, the network language model, where when we ask a question, what is my default route? We can look up the data in the vector store, which might be the mathematic representation of the JSON output of the routing table. And then it would come back with augmentation to help generate a better output. Now keep this in mind. A large language model is a closed book exam. It has a knowledge cutoff date, and whatever it's been trained on is the only data set that it has access to. So it's sort of like a human when we study for an exam and we write the exam, it's just us and the piece of paper and the pencil. In this case, instead of an exam asking us a question, it's a human asking the LLM a question. I would argue RAG turns this into an open book, where now the LLM has access to a vector store with, ideally, the information to better answer the question. So if I asked a closed LLM, what is my default route? It has no idea. It's going to hallucinate, or it's going to give me word salad. At best, it might tell me what a default route is and how to find out on my system, but it's not going to have the requisite knowledge to answer my prompt. RAG can overcome this. However, RAG has limitations. So if we took the Book of Cinderella, for example, and uploaded it to this process as a PDF, it would kind of work. And you could ask, what the names of the evil stepsisters were, and that would work. But if we asked it something like, how did Cinderella get to her happy ending? The top retrieval values, known as K values, usually set to 10 or maybe 20, the number of chunks, the number of vectors to include in the response is not going to be enough to answer that philosophical type question. So recursive abstractive processing for tree organized retrieval, and that's the key here, is that we're going to organize the data, and it's still chunks of text, and it's still vectors. It's just organized in a different structure instead of a vector store. Now, if anyone's from the networking world, and I'm sure a lot of you are, does the raptor tree on the image on the left not look just like a well-organized data center with a core and a spine and a leaf layer in a partial mesh non-blocking topology, a CLO topology? So the bottom layer, the leaves, is going to be made up of the chunks of text, the sentences. And now I'm explaining this because we're going to tie it back to Selector. What happens is we cluster those chunks of text. So 1, 4, and 5 might be everything about the pumpkin carriage. 2 and 3 might be everything about the glass slipper. 3 and 5, everything about the mice. Similar to how Selector is going to take logs that we mine and metrics that we have available to us and cluster them together. Now in Raptor, we use LLM to generate summary layers, automated summaries of these clusters. Now we do this recursively all the way to the top until we run out of tokens or run out of text and run out of things to summarize. So now when we ask the question about how did Cinderella get to her happy ending, we can evaluate this massive tree of summary layers, which should have enough augmentation capability to improve the generation of the output. Now please note this is much higher computational and GPU resource requirements to build a tree versus a semi-basic RAG with a vector store. Next, and more recent, is something known as graph RAG. Now, I believe you go to microsoft.com/graphrag, that's where I got this image. They have all kinds of wonderful papers, code, open source repositories. They're really pushing for a graph RAG solution where we create this massive knowledge graph that is made up of global communities, sort of the larger dots that you see sporadically, and localized communities, the much smaller but yet clustered chunks of knowledge. Now we're going to look at graph RAGs and the the knowledge graph and the clustering and hyperclustering throughout Selector when I get to the use cases. Now before I move on, if you're looking for RAG solutions, Raptor solutions, graph RAG solutions, please just visit my GitHub repository, github.com/automateyournetwork, and get started. Anything that's called Buddy is RAG, anything called Raptor is Raptor, and anything called Graph is Graph RAG. Now let's look at a fine-tuning example. Now that we've understood sort of different retrieval augmented approaches, now we're going to connect the dots to fine-tuning approaches to build into RAFT. So what I'm going to do is go into the fine-tuning center in platform.openai.com, and I'm going to look at this example where I've used this base model of GPT 3.5 Turbo, and I've fine-tuned it into a personal routing table model. So this really has taken this JSON data set, and let's look at the data set real quick. So I have 250, I believe. Yeah, 250 or so different prompts. So I have a system, a user, and an assistant. The system is always your computer networking expert specializing in network routing tables. The user is a question, and the assistant is the correct answer to that question. Now, I did not write any of this. What I did was I used RAG to generate this data set, this JSON-L file, meaning I gathered the routing table as JSON, did retrieval augmented generation, and my prompt was, could you please generate 250 questions with correct answers from this JSON data set? Always use this system. Boom, it generated the data set with correct answers and a variety of questions, which I uploaded, right? Create. And then it got fine-tuned, and here's the training information, and that the job successfully completed after about 30 minutes. Now this cost me about 12 cents to make. So let's go into the playground, and I'll show you what I mean by a fine-tuned model. So we're going to pick GPT-4o over here and say you are a networking engineer who specializes in routing. Now on the right is my fine-tuned model, and we're going to say, what is my default route? Which may or may not have been one of the questions I used to fine-tune it. In this case it was. But on the left you can see it's kind of a word salad, how to find your default route and what a default route is. But my fine-tuned model, that I've used retrieval augmented generation to generate a data set and fine-tuned this GPT 3.5 model, knows my next hop's IP and what interface it uses. Now to prove sort of the inference, I can say stuff like, is gigabit Ethernet 1 used in my default route? Now I haven't tried this question, but it should say yes. Yes. Right? So it can infer now questions outside of that data set here that I was talking about. So, because I don't ask that specific question here as one of my questions. So keep this in mind, because what we're going to look at now is how Selector makes the world's first network language model using this sort of retrieval augmented fine-tuning approach. So we start with an open source model as the base model. It's very important to understand that Selector is not really using ChatGPT in the cloud here, or Claude, or any public cloud service. Truly is a private, localized model. In our case, Llama 3.1. Now this is a large language model that's been trained with English data to understand English phrases primarily. And I'm sure a lot of you have played with Llama 3 or 3.1, extremely highly capable open source models from Meta that compete with ChatGPT at scale. Now, keeping the fine-tuning in mind, the first outer layer of training and fine-tuning that Selector does is to convert the English sentences, why is Wi-Fi down in Denver, into Selector's SQL interface. Now Selector, the name of the company, comes from SQL, select statements, and that we've used natural language to completely eliminate the need to learn a customized domain-specific SQL implementation. You just ask it your questions in a human language, and this outer band of fine-tuning will transform it into our language. The next thing we do, which is really exciting, is wrap the customer data, those the mined logs, the metrics, all of the information that we've normalized and correlated, right? We can use this information to create an outer band of fine-tuning, which results in a network language model customized per customer, right? So each customer gets the two inner layers, and the outer layer is specific to their network environment or their application environment, their infrastructure, right? So we can deliver this at scale and include the different domain-specific, enterprise-specific information in the fine-tuning outer band. Right, so show me errors in Ashburn, hits a translator, using the LLM, hits the fine-tuned model, the network language model, which returns back into a SQL query, and then we respond with human natural language. So let's look at some use cases. First of all, we're going to look at some correlation and root cause analysis. And I really like this example because we've got multiple BGP sessions associated to some Marietta route reflectors, and those route reflectors connected to Marietta. So look at all those events at the top. We've got hundreds, if not thousands, of BGP status problems, which turn into BGP status problems. But then we filter it down using the correlations, and we can see that there's major traffic shifts happening as a consequence of the control plane instability, but it actually all gets boiled down to a wire traffic change. The single root cause on the single router ID and the impact it's had all the way upstream. Now imagine trying to do this, understand this outage without these insights. Like, where would you even start? Whereas now you know exactly where to look and exactly how to resolve the issue. Now again, correlated alerting. So this is a sort of another correlation graph. We talked about the graphing earlier, where we have some interfaces go down, which has caused OSPF interfaces to go down, which has caused OSPF adjacencies to go down. So we can see that the causation, right, an interface down event on some host name likely caused the adjacency to go down for that host name. And we can see the complexity of the SQL query that's all been boiled down into human language again. Now this is an application example, and I really like this one because what we're going to find out is that there's been, right, we're hitting API latency rules, which is also triggering read latency, disk rewrite rules, page faults, memory free rules. Right? We can see the top labels of the host name and the IPs involved, but we can see that there's significant user facing latency, and this application stack's going to lead to SLA violations. Well, this actually turns into this smart alert. Right? Here's a description. 95th percentile endpoint latency for app has risen from 68 milliseconds to 141 milliseconds. Right? The node memory free rule has likely caused all of these cascading failures. So we know that it's we've run out of memory on this node in the stack, which is causing API latency with the machine learning, the clustering, the graphing, right? It's remarkable. I know this might seem like magic to you, right? But it does turn into these smart alerts. We've got a root cause correlation alert. We had an optic fail, which caused BGP sessions to go down, including clusters and ports and backbones, right? So we've had an optic, and here's everything that's related to it. One single alert, one single smart alarm with hyperlinks into the dashboard for a deeper dive. Again, an interface goes down, so we lose ISIS, we lose LLDP, we lose OSPF, we lose all this stuff because of a single interface down alert and all of the impact that it's had, right? Now this is the one I call the tornado. Look at these events. Look at the mesh and the graph that we've created and the knowledge connections and the correlations to go all the way down to, right, a configuration change. And we can see that Joe, unfortunately, caused a lot of network events, right? A configuration change on a certain device has caused a lot of network events. Different protocols were affected across the network and caused traffic losses. 43 correlated events down to the metro and the region using the metadata to describe the impact. Now in today's NOC, today's operational world, right, you may have heard of panes of glass, 38 dashboards for metrics, 15 for logs, 50 for applications. I call these glasses of pain, okay? Because at 2:30 in the morning when there's hundreds of alarms and they start to fire, it's just chaos, right? You start chatting with other operators. What's going on? I'm buried in alerts. No idea. All my apps are complaining. This is a real mess. I'll start looking here. You start looking there. Let's start letting people know, right? Instead, we can focus all of this and concentrate it into machine learning and artificial intelligence so that you can simply ask it to show you Wi-Fi events, for example. Or so that you get a smart alert at 2:30 in the morning that takes all of those glasses of pain and boils them down into a single root cause and correlated impact. So normally I would do Q&A, but since this is on YouTube, please check out Selector AI. Please follow me on Twitter. Please follow them on LinkedIn, me on LinkedIn. This is a new revolution in operations, right? AI ops is truly a legitimate thing that is here, and I think you should explore it. I think you should get your hands dirty with RAG and Raptor and graphs and really try to incorporate and augment your operational existence and your human experience with artificial intelligence.